Over the last 25 years, I've had the privilege of interviewing and highlighting some truly interesting people. Everyone who is anyone, both the famous and the infamous, from presidents and their first ladies to kings and queens, movie stars and pop stars, captains of industry, heads of state, sports personalities, innovative entrepreneurs, and some pretty fascinating everyday people. Today, I'd like to introduce you to Dr. Stephen Wheeler, an award-winning professor and data scientist who attributes his success to his faith, to hard work, to passion, and to dedication. Well, I have to tell you, Dr. Wheeler, that sounds like a pretty good person, and I'm happy to talk to you today. Dr. Wheeler, what made you decide to become a teacher, which I do believe is God's work on earth?
Yes, I completely agree. It is somewhat of a calling, but it is also there are several aspects. One of which is the camaraderie with faculty of like mind and like interest, research domains, and so forth that parallel. So that's a another big factor. But I think it all comes down to passion and to somewhat of a calling, as you suggest.
So, Dr. Wheeler, what interests you most about sort of the general concepts of machine learning and data science? I'm a bit of a nerd, so you got to give me a little bit of a master class.
Mm-hmm. Well, the interest from my perspective is the fact that I've always been and had a fascination in the human mind, how we rationalize things, how we learn. Data science is a combination of machine learning, but also the application of machine learning in terms of its utility within industry and other venues. The fascination that I have with data science is its utility. It is very useful in this modern age for making predictions, for diagnostics, for many levels of application within the general sphere of human domain. For example, we can train computers to recognize from images whether a cancer is present or some other disease process. We can also train computers to detect before we have a problem within a system when a failure might arise so that it can be treated prematurely, and many other aspects. But to me, the main interest that I have is in the way that machines now learn. Was based on some very early research going back all the way to 1943 when McCullough and Pitts first suggested that machines could be trainable. They could be sort of an emulation of the human mind to some extent. And then Donald Hebbs, he suggested that there is a learning algorithm called backpropagation where we can train these devices, and then the development of what is called the perceptron. The problem with the perceptron was that it could not distinguish an exclusive OR. Now, what is an exclusive OR? Well, an OR says it is either and both, two conditions, either one being true, the output is true, or both being true, the output is true. An exclusive OR is one where it is either one but not both. So it excludes, it is just an exclusive OR. Well, perceptrons couldn't learn that. However, later they came up with a solution, and that is adding internal layers, hidden layers within the architecture. And those hidden layers allowed it to be able to learn even to the extent of an exclusive OR. And now we have what we call deep learning models. And what that means is that they have a lot of hidden layers between the input layer of neurons and the output layer. And having that is a fascinating development because it allows this field to be somewhat boundless. And there are three main models for machine learning, which is the supervised model, where we give training data to the model, and it learns by example. The other is non-supervised, which is where it learns on its own. It can do grouping of things together based on their proximity, and that doesn't require training in terms of a data set. The third model is called reinforcement learning. Now that's an intriguing model because I don't know if you have heard, but Google bought DeepMind, and DeepMind was working on reinforcement learning. And what they did was to train the model by letting it play itself, and then reinforcing the good choices and eliminating the bad choices. And that is what was used in what was called AlphaGo, where the world's best Go player was defeated by that learning algorithm. And it was called AlphaGo. But also they trained it further into the game of chess. And now AlphaGo has beaten every human. And it's not called AlphaGo anymore, though. It's called AlphaZero. And it's beaten every human and every chess program that plays above the international grandmaster level in competition. So it's really a great step forward for machine learning.
I got to tell you something, Dr. Wheeler. I know that these brilliant geeks like you get fascinated and are excited about that. But for those of us who are laymen and who watch things like The Terminator and War Games, it scares the bejeebies out of me, okay?
Right.
So speaking on behalf of the laymen in our audience, do you think that there are misconceptions, sort of like me being a dingbat here, that the general public has about true artificial intelligence and how it really looks in practice?
Yeah. In psychology, there is a human malady, which is known as idiosavantism. In vertical intelligence, they're very sharp, but in horizontal intelligence, global intelligence, they don't do well at all. A movie was done about that called Rain Man, and Tom Cruise had a brother that had this syndrome, and he didn't understand it. But what he had was vertical intelligence. All AI models today have narrow AI. They're really good at one area, such as playing chess, playing Go, driving a car autonomously. But broadly, horizontally, their knowledge domain limit is limited to the area in which they are focused. And that goes for all AI today. They're just linear models, vertical. Now, the other is called AGI, Artificial General Intelligence. And Ray Kurzweil with Google has been working on that for some time. And that might be a little more dangerous because it would have the ability to learn on its own from a very horizontal world, a very broad world. But still, it doesn't have any self-motivation. It's not self-aware. And so therefore, until a system becomes self-aware, it doesn't have the ability to reason that it needs to do up within a moral framework.
Wow.
Or operate outside of it, because it's not self-aware.
Dr. Wheeler, that sounds a lot like one of those movies I've been talking about.
Yes. And the other is called the singularity, where it's super intelligent. But I don't think that we'll get there until the machines become self-aware. And I do not believe that that's possible and without quantum AI, without getting into the quantum aspects of machine learning, which I'm also very interested in.
So I understand you've written some academic papers on the whole concept of alpha beta. Is it quiescence and quantum computing?
No, it's really not in quantum computing. It is research in linear computing. That is to
Okay,
say,
so you got to give us a little bit of the bare bones look at what this entails, because again, I'm a little bit educated because I wanted to be able to sound smart when I chatted with you, but I need your help.
Right. There are two models of AI. There's what we call dynamical models, that would be machine learning and so forth, artificial neural networks. The other model is called linear symbolic AI. Now, what is that? That's where we write the programs to solve specific problems using a symbolic code, machine and computer languages. And that is what I did research in Alpha Beta. Now, what is that about? Well, back in the 40s, there was a book that was co-authored by Dr. John von Neumann and Oscar Morgenstern called The Theory of Games and Economic Behavior. And in it, he introduced an algorithm called Minimax. And what is that? That is an algorithm that says, if I do this, what will be the consequences? And then looking at those consequences, what would I do in return if the opponent does this other thing? So if I do this, then he might do this, then I'll have to do this, and so on. It's called Minimax. And the way that it works such that it looks for the minimal loss and the maximum gain in whatever its actions are. It's called Minimax. It's a theorem that came out of game theory. Now, it has been the core of every chess program and every program that makes decisions that have consequences since its introduction. In 1950, Claude Shannon is also known as the father of information theory. He proposed how one might write a chess program using Minimax. If the computer does something, what will I do in return? And then what will it do in return to that? The problem with that is that it generates what's called a game tree that branches in every direction that the game can go. And for the alternatives to the consequences for someone taking an action, for example, the computer taking an action, has to be weighed out by all the possible actions that the opponent can take in response. And what happens is that tree grows exponentially very, very quickly. So the number of choices at any one level looking forward, if I do this, then the opponent might do this, then I will have to do this, this, or this. It grows at a rate of how many choices there are to the level forward in time that you're going to look. In other words, how many moves are you looking ahead at these? And it grows exponentially. The width raised to the power of the depth, how far you're looking. And that number gets extremely large very quickly, into the trillions. So how can you control it? All right, so alpha beta is a pruning mechanism that says if we put the best moves first, then when we find one that's not as good as one we've already tried, we can prune the game tree. We don't have to look at all the other alternatives. But the problem with that is it even grows when we look more than, let's say, 3 moves ahead. Then we have to do something else, and that something else is called quiescence. So what is that? It is where if we only look at the important moves, captures, promotions of a pawn to a queen, for example, and king and check situations, but only to a couple of levels. And this is done one level at a time. It's called quiescent phase of alpha beta search, or It is also known as singular extension, and that was done in the Deep Blue chess program that beat Garry Kasparov in 1997.
Dr. Wheeler, I'm going to take you out of the weeds for a minute and
Okay.
ask you, how do you view technology's role in the development of our society?
Okay. I see it as a one-way street. Technology, you can't stop technology.
Mm-hmm.
The idea is it's also a two-edged sword. And one has to control the technology, and so that we don't become an Orwellian society. In that, in order to protect us in airports and so on, we have surveillance.
That's the concept of that's the concept of Big Brother.
Big
It's
Brother,
always
exactly.
looking. Mm-hmm.
Exactly. And so that is something that I think we need to control. It can be very beneficial for society, but it has to be managed, because after a point, it becomes the other edge of the sword. Instead of the helpful edge, it becomes the invasive edge of the sword.
I understand that completely.
Right.
I read that you said at some point, when opportunity knocks, you answer the call.
Right.
Give me an example of when that actually happened.
I applied for the NASA program for astronaut back in the 90s. And because of the problems that NASA was having with funding, and also they had a couple of mishaps, they put that program on hold for a while. However, it did allow me to get exposed to an area of research that they were engaged in for the, at least it's supposed to be at this point, 2033 manned trip to Mars. We start out with Orion and Artemis going to the moon, establishing a base, and then going on to Mars. That's the plan. So, but you can't do a Mars venture without understanding what the limitations are. So, at the Mars Desert Research Station in Utah, I was elected to be the commander of Crew 88 in the Mars Desert Research Station, doing research for micropaleontology, for exobiology, and various aspects of that would be required on Mars. And so that was an opportunity that knocked, and I immediately leaped in that direction.
Absolutely.
With a proposal for my research, and the fact that I had a PhD, they decided that I would be best for the commander of that. And since I'd already applied with NASA previously. So I consider that a good example of an opportunity realized.
And not only did it knock and you answer the call, I mean, just that's magnificent. Congratulations. That's a fantastic opportunity. Sir, what are your plans for the future?
Well, my plans for the future are to continue in research. The area of research that most interests me right now is quantum computing. Where my research interests lie within that domain is in quantum machine learning and what is known as actually quantum consciousness. Now, my theory is that that if the brain is working on a quantum level, it entangles with what we are observing as the wave and causes it to collapse into another form. If my theory is correct, that is that we can develop quantum consciousness by quantum neural nets, that would explain why we get this mysterious collapse of one state, subatomic state, into another upon observation. Anyway, I know that's a bit of a broad explanation.
I know, Dr. Wheeler, I'm sitting here going, I consider myself to be smart, but you're zooming right past me on that one. That's why I'm glad there are people like you who do what you do so that we all can benefit from it. Finally, just let me come to a conclusion. We've talked a whole lot about what is your passion. What's the one thing you'd like the viewer of this video feature to walk away with today?
Well, I have thought on that, and what I would really like the viewer to walk away with is the fact that we have to keep our thoughts and our imagination unbounded. So I would say that what I want them to think about is just as I have speculated on what causes the collapse of subatomic states, for example, into other states. This is something that I think is relatively new, and so you have to think outside of the box. Don't bound yourself with other people's ideas, but think outside of the box. Expand your thought processes so that you are really expanding your area of influence by thinking outside the box. For example, the quantum effects are something that we're still learning about, but you have to, you don't have to understand it completely in order to make it useful.
Right.
So I think that's what I'd like to convey.
Yeah, you don't have to understand it completely to find it fascinating. Yes. And to know that any advancement is going to advance humanity, which is at the end of the day, a very good thing.
Right, exactly. And many people, I talked about Copernicus and Galileo, but also Einstein. He did thought experiments, and he came up with general and special relativity that he allowed himself to think outside. I'm using the current parlance,
Yes, I'm pretty sure Einstein didn't say I was thinking outside of the box, but I think we get your point on that one. Dr. Wheeler, thank you so very much for your time today. Thank you for giving us a bit of a masterclass on an area that is absolutely exploding all over the world and helping us to think outside of the box.
Okay, well, thank you so very much, Star. I've enjoyed the interview so very much.